Okay, as I told you, we are a little bit late with this course. So hopefully I'm going to, so this is probably not the last lesson. Okay, I'm going to use probably today and Thursday to finish off all the subjects here. Essentially, we want to look at the structure of the premixed flame. Okay, I'm going to be talking about premixed flames a little bit more, and then essentially derive two basic facts. Okay, the thickness of the flame. Okay, what does it depend on? Okay, and most importantly, the propagation speed. Okay, as I told you, the quantity that we cannot determine through the Rankine-Hugoniot analysis. Okay, we're going to determine with this theory here. Okay. So, as I said last time, I'm trying to set the stage, let's say, for laminar flame theory. And one thing that we defined was the deficient reactant. Okay, so it's very useful to think of this flame as having or operating, let's say, in a off stoichiometric conditions. So if we are in lean conditions, the deficient reactant will be the fuel. If we are in rich conditions, the deficient reactant will be the oxidizer, so that this Y here is always the deficient reactant. So downstream of the flame, it's always completely zero, depleted, okay? Now, very important definition is this, the flame speed, okay? Now, that's going to be the crucial definition. Let me just, maybe I can make this thing a little bit thicker, whatever, which is it's Vn, okay, Vn plus on the fresh side, okay? So remember, this is the plus side, this is the minus side. So what it is, it's defined as the flow velocity relative, okay, to the flame. Okay, so it's Un plus, which is the flow velocity in the laboratory frame, minus the velocity of the flame itself. So U plus is clearly UU minus Wn. So in a flame stationary frame, okay, the flame speed is exactly equal to the incoming flow, okay, the fresh mixture flow velocity. So you essentially, you keep this flame stationary, okay, at zero velocity here, and you have a velocity here of the fresh mixture that is enough to stabilize the flame, okay? So this flame stays stationary. So in a way, the flame, you have to think of the flame as a gas dynamic reactive, okay, structure or solution, okay, that essentially will consume, okay, the mass flow of fresh mixture that is being fed, okay, but there is only one and one only mass flow for that incoming flow that will stabilize the flame. So it has its own, let's say, propagation speed that we will see will depend on a series of phenomena, okay, such as the fusion of heat in species, okay? Now, let's see what else we can, okay. Another thing that we can say is the fact that the Rankine-Hugoniot theory really told us that deflagrations are, let's say, in the regime where the Mach number of the incoming flow is very small, right? So remember, in the PV sort of diagram, the Rayleigh lines were extremely shallow, okay, extremely, so with a slope that's very, very small. Now let's see what mu is. Well, mu is, well, the velocity of the incoming flow, UU, okay, divided by the local speed of sound, right? Now, in a wave stationary frame, we saw that UU is just SL, the flame speed. Okay, so in general, for deflagrations, this is a fact. Okay, that the flame speed is extremely smaller than the local propagation, the speed of sound. Okay, the sound propagation. We have also seen from the Rankine-Hugoniot, okay, analysis, that being the Mach number very small, okay, the pressure, okay, jump is extremely small. Okay, so the pressure jump is essentially this distance here. So we can say that premixed flame is near isobaric. Okay, now the two things are completely related. The Mach number is small and the flame being near isobaric. We can see this if we consider the momentum equation, okay, in one dimension at steady state. So we just essentially take the bare minimum, okay, for the conservation of momentum, which you can write down very easily as rho u du dx, and then equals minus dp dx. Okay, the gradient in pressure with a minus sign, okay, is equal to essentially the rho du dx term. Okay, how can we use this? Well, generally, what you usually do with these equations, you non-dimensionalize them. So you take, for example, non-dimensional quantities, such as non-dimensional density, and you define them as the density divided by some representative density. In this case, the representative density will be the upstream density, okay? You can still see, right, everyone?
Sí.
Okay, so the same, when you non-dimensionalize an equation, you have to do this for every single variable. So again, here, U will be non-dimensionalized with respect to the fresh mixture velocity, so the upstream or unburnt velocity, and so is the pressure, okay? So the tilde quantities are non-dimensional quantities, okay? So if you plug those into the momentum equation, it's very easy to see that you get something like this. Rho, you have a group of terms, rho u, u squared divided by pu, okay? And then you have the non-dimensional equations, essentially. Rho tilde, u tilde, du by dx, okay, equals to minus dp by dx. I haven't non-dimensionalized the space because clearly it cancels out. Okay, so I'm just doing a very fast treatment here. Now, what does this term mean? Well, if you use the equation of state, it's very easy to show that this is essentially gamma Mach number squared. So it's the unburnt Mach number squared, okay? So you can see that in some sense, the gradient of the pressure, okay, will be of the order, you see, this is order 1, let's say, because these are all non-dimensionalized, okay? So it's of the order of the Mach number squared, okay? So generally speaking, it's a squared, not the Mach number. So the Mach number is already a small parameter, okay? So the Mach number square is even smaller. So that's why we say that the flames are near isobaric, okay? And you'll be able to see this in all sorts of ways, okay? So essentially across a flame, you don't have, okay, a variation of pressure. You have a very small variation of pressure, okay? You always have some variation of pressure because otherwise the momentum equation tells you that there is no movement, okay? So clearly in gas dynamics, gradients of pressure are the, let's say, the engines, okay, of movement, okay, the sources of movement, of flow, of fluid flow. But again, it's very small, okay? And in fact, it is because it's a very small, the Mach number is very small, this is really, it gives us a chance to simplify things, let's say, significantly, okay, in the equations. And I'll show you what is usually done, okay, when we want to study things like premix flames, okay, in computationally, so in computational fluid dynamics, okay, it is unreasonable, okay, to use the full equations, the full Navier-Stokes reactive equations that are compressible for a compressible flow. It is more convenient to operate some sort of simplification, taking advantage of the fact that the Mach number is small. So if we rewrite this non-dimensional equation, okay, like this, because the Mach number is small, what we can do, or what is usually done, is one can think of expanding all of the variables, okay, non-dimensional variables, in a series where the Mach number, okay, appears as a parameter. So you have essentially a leading order, okay, so this is the pressure, okay, will be represented by a leading order term, and then a small, let's say, contribution of the order of the Mach number, okay, squared, plus negligible, okay, terms, okay? And the same thing you can do for density, okay? You see that I'm essentially introducing a zero order and a first order, okay? And so on, etc. Now, if you plug those in this equation, so you just take the zero and first order and you plug them in the equation here, you're going to get, of course, I'm doing a very, very fast here. I'm going to skip all of the steps because what's important here is to understand the basics. You obtain something like this. So you have essentially the equations that are rewritten in with only the zero order term, and then you have essentially dp0, okay, dx minus mu squared dp1 dx. Now, note that mu squared essentially morally is your epsilon, a very small parameter, okay? Now, what we usually do here is you look at this equation and you realize that there is an order one term, whereas these are all order max squared, okay? You see that there is a max squared here and a max squared here, okay? So essentially you have order epsilon here and here and order 1. So what you usually do, and if you remember, we've already done this, okay, with regular perturbations and in singular perturbation also theory, you compare, okay, equal orders. So you extract the order 1, okay, terms, and all you have here is, and you compare left hand side and right hand side, okay? And so you have that the gradient of the leading order pressure term is equal to 0, okay? You get this, right? So it's not balanced by anything on the left hand side. So because on the left hand side you only have order max squared. And that is a very interesting thing because it really confirms the fact that the so-called thermodynamic pressure, the one you would use in your, say, equation of state, really has no gradients. It's uniform, okay? So even in the presence of a premixed flame, okay, you have a basic zero order pressure, the bulk, the real pressure that you're doing, that you are, let me explain this a little bit better. So it's the thermodynamic pressure, trying to do this fast, but okay, it's the leading order pressure. So say, for example, you have premixed a premixed flame at 20 bar. This would be the 20 bar, okay? The bulk, the actual leading order of the pressure, okay? Now, this other term here, okay, it will be a small perturbation of that, okay? Now, the equations tell us that the thermodynamic pressure, okay, even in the presence of a flame, will be uniform and constant in time, okay? So P0 is uniform in space and constant, which is something that cannot happen, okay, whenever you have, for example, a shock wave, okay, which requires high Mach numbers, okay? So this is a typical situation of low Mach number flows, okay? So these are the low Mach number equations. And you also have an order Mach squared, okay? And so here and here that you have to compare. So it's essentially gamma. The Mach obviously cancels, and you have rho 0, u 0, okay? So you have essentially a form of the momentum equation, okay? Your Navier-Stokes equation, okay? Which only retains, okay, the higher order pressure. So what happens is that the fluid flow kind of sets into motion, okay, only by means or as a result of variations in the higher order pressure, okay, which is very important because what you can do, okay, in low Mach number flows is that you can completely forget about things like acoustic waves or shock waves, which usually propagate at very high speed. All you have to do essentially is have a constant pressure, okay, and then essentially solve the Navier-Stokes equations with this essentially so-called hydrodynamic pressure, which is not the thermodynamic pressure. Okay, which is simply used as a source of movement, okay, as a reason of movement for the let's say the zero order variables, okay, velocity and density. What this means is that you can actually, in computational fluid dynamics codes, you can actually use, for example, increments in time, delta t, that are larger, much larger than compressible flows, simply because you don't have to worry about the propagation, the acoustic propagation, okay, of pressure waves, okay, moving at the speed of sound. Okay, so we have a complete decoupling, okay, of essentially, as you can see here, the zero order pressure and the density. So you don't have, so it would be as if the propagation speed of the acoustic waves is infinite, okay? So you actually separate the two phenomena, which is very, very convenient, okay? So I'm just going to give you, this is as much as I'm going to give you in terms of the so-called low Mach number equations, okay? Let me write this here, low Mach equations, okay? Some people prefer to use the complete Navier-Stokes equations for numerical reasons, even if they know that the Mach number will stay very small, okay, in typical combustion chambers, okay? You have to remember that these are the situations that you always have in combustion chambers, okay? Aeronautical combustion chambers, gas turbines for power generation, okay? You always have a situation where you have a deflagrative regime, so a regime where you have essentially deflagrations, or at best, you could also have non-premix flames, but the core of the matter is that the Mach number is kept very, very small, okay? It's usually very small. So you can think of combustion chambers as having essentially a uniform thermodynamic pressure, okay, P0. And of course, there's going to be some movement, okay, and this is going to be caused by the hydrodynamic pressure, okay, but clearly there is not going to be any shock waves or anything like that, okay. In fact, the Mach number is kept low, if you remember something about propulsion, because we want to limit the losses in total pressure, okay, which is another concept, okay? Total pressure as in the capacity of the flow to do work, essentially on, well, in an aeronautical engine, of course, on a turbine, okay? If you lose that pressure, clearly you're losing a lot of the capacity, okay, of this flow to do work. But in this case, you see that there is a, well, this can be considered as a total pressure, which stays uniform and constant, okay? Now, so in the following, we will neglect any sort of spatial gradients, okay, of pressure. And usually what we do with premixed flames, okay, to look at the structure of the premixed flames is to look at 3 levels of detail, okay? For premix flame. What do we mean by this? Well, if you look at the flame from very far away, okay, the flame will be essentially zero thickness flame. Or we can call it a gas dynamic discontinuity. So it's essentially the very same thing or level of detail that we saw with the Rankine-Ogonio theory, okay? You have an interface separating far upstream and far downstream states, okay, that you have to match through conservation of mass, momentum, and energy, okay? So that's the Rankine-Ogonio analysis, essentially, okay? Now, if we get a little bit closer, we have a second level of detail of the flame, okay? We can call it a transport dominated level, where we actually unveil part of the structure of the flame. Not all of it, okay, but part of the structure. The phenomena of essentially convection and diffusion. Essentially here in the first level, you only have convection, right? Okay, you only have essentially an upstream and downstream velocities, okay, and that's it. There is no diffusion, there is no thickness, okay, there is no structure to the flame. Now we're going to move a little bit closer, and now we're really unveiling this phenomenon here of transport, which is diffusive transport, okay, which we were not taking into consideration in the Rankine-Ogonio analysis, okay? This zone that we reveal is generally is called the preheat zone. Okay. What about the reaction part? There is definitely, or intuitively, there is going to be another zone of this flame that will involve chemical reactions. Well, in this intermediate level, what we do is we only reveal the larger structure, which is typically the structure that has to do with thermal diffusion, essentially. Thermal diffusion and mass diffusion, okay? The preheat zone. But the reaction zone, remember that the reaction zone, the reaction times are always smaller than the diffusive times, okay? So the reaction is always taking place in a very small boundary layer, in this case, a spatial boundary layer, which we can still consider as being zero thickness, okay? So we can say here, reaction zone is still of zero thickness. I'm going to draw now pictures so that it's going to be clear. Now, if we move even closer, okay, we have essentially the complete structure of this flame, okay? So we're going to consider essentially the preheat zone that we saw before, plus a reaction zone or reaction layer, okay? So both of them will be of finite thickness. In particular, this will have a thickness, we're going to call it LD, and this will have a thickness LR. So in this case, LR is essentially zero, okay? So we're going to see essentially the complete structure, which is composed of a preheat zone where there are no reactions, okay? But there is diffusion. So it's essentially an area or a zone upstream of the reaction zone, okay? That will be heated up, okay, by the reaction itself, by the sort of the hot side downstream, okay? And when the temperature is high enough, the reaction will take place, okay? So it's downstream of the preheat zone, okay? We're going to see now all of this in detail right now. So let's take a look at the first level of detail. So we've already kind of seen this in the Rankine-Hugoniot, right? In the Rankine-Hugoniot analysis. So what we have in a wave stationary frame, we have a surface, okay, or a gas dynamic discontinuity, not moving, so it's stationary. We have an upstream velocity which is equal to the laminar flame speed. And we have now profiles, for example, of the deficient reactant of the unburnt side, okay, that is completely depleted downstream, okay? So the burnt side, on the burnt side, sorry, this is B. The burnt side, the concentration on the burnt side is 0. And then on the other hand, we'll have a temperature, okay, of the unburnt side, and then downstream we're going to have a burnt side temperature, which is much higher, okay? TB here is generally known as the adiabatic flame temperature. Let's see why. Well, if you remember, again, the Rankine-Hugoniot analysis, the jump in static enthalpy, okay, we had determined already, and it had this form here. The sum of the specific volumes times the difference in pressure. Okay? Now, generally speaking, you will never neglect the difference in pressures, okay? Think of a detonation, obviously. You cannot, obviously, neglect this. But in a deflagration, what we can do is we can say, well, look, the burnt pressure will be approximately equal to the unburnt pressure, because we said that we're going to neglect pressure gradients. So you can see that for very low Mach number flows, for isobaric combustion waves, essentially this term, this jump in static enthalpies is really 0. Okay. You couldn't do this, okay, clearly in a detonation, because you have the pressure, you have essentially a part of the energy equation that has to do with the work done by the pressure forces. But here, clearly, there is no such thing, okay? And so we can consider, essentially, if there are no heat losses, but we've already excluded all heat losses from the very beginning, an adiabatic, a fully adiabatic flow, okay? And if you remember how we expressed this jump, okay, in static enthalpy, we said that it was minus QC, so this is a heat of reaction, and then plus essentially CP and the difference in temperatures, okay? So if you rewrite this in a premix flame, you can see essentially this, that the heat of reaction, this is equal to QC, that the heat of reaction is essentially fully used, okay, to increase the temperature of the products, okay? So what you do here is you have an incoming flow at temperature TU, which is heated up to TB through the heat of reaction. There's another way in which you can write this. TB, okay, the burnt temperature, the adiabatic temperature, or flame temperature, so we can call it T adiabatic, okay, sorry, this is adiabatic, okay, is equal to what? To the unburnt temperature, okay, plus the heat of reaction divided by Cp. okay, which is rather simpler than what you have in detonations. Let me just open a little parenthesis, okay, because I really want you to use, for example, social media, like not social media, like the internet, like YouTube, because there's a lot of material there. You may be wondering, okay, but if you are always using premix, well, deflagration, sorry, premix flames in combustion chambers, such as aeronautical combustion chambers, and generally speaking, low Mach number flows, but you do that also in rocket engines, where the Mach number is kept low, at least in the very beginning, okay, of the mixing and combustion zone, okay, then it will be accelerated clearly through the nozzle. But again, there is the same concept, okay, that you can use low Mach number flows also in liquid rocket engines, okay, combustion chambers. So if you always have a deflagrative regime in these combustion chambers, what about detonations? Are they ever used in engines? Well, first of all, you may be familiar with the word knock, okay, which is a detonative phenomenon that you have in internal combustion engines, so in cars, that you need to avoid. So this is something that you need to know in order to avoid it. Even more interesting than that, you can look up on YouTube something called detonative engine. Okay, or rotation detonation engine, or something like that. Okay, now you can also use the detonative mode. Okay, although it's much less. It's a little bit far less easy to control, and there are some videos of both computational fluid dynamics, okay, as well as experiments where there has been attempts to stabilize detonations, okay, in an annular combustion chamber. So it's essentially cylindrical. Okay, it's an annular, okay, combustion chamber where essentially the detonation wave is kept under rotation at a very, very obviously fast rate, so that fresh mixtures of fuel and oxidizer can burn. Now, it's going to burn essentially very fast, okay? The advantage, the claimed advantage, is that we're not going to have essentially a constant pressure combustion, but it's more of a constant volume combustion. And it can be proved that there is an increase in efficiency, okay? And you can see this through your thermodynamic cycle analysis, okay? So take a look just to know that, you know, there are other alternatives, at least in theory, that you can use to alternatives to deflagrations. But deflagrations are clearly the most common combustion mode, okay, even in your kitchen, okay, so as we've seen. Another thing that we can look at is the velocity jump. You can hear me, right?
Sí, sí.
Okay, sorry that I keep on asking, but So I will skip a few steps here. You're welcome to fill in the gaps, okay? Because we've already seen most of it. If you take the conservation of mass, okay, written in this form, okay, we can rewrite it with the definition of V. The definition of V is essentially U minus W, okay, which is your velocity of the flow and minus velocity of the combustion wave. This is equal to 0, okay? So essentially, this is a jump between the burnt and unburnt quantity. Okay, so we can write it like this, rho B, etc., minus rho U, right? U minus WN, okay? This is equal to 0. So you can rewrite it as rho B UB minus rho U, okay, equals to, sorry, let's write it this way, better still. WN, and then rho U minus rho UWN, okay? Now, you can subtract, for example, rho B UU and do some sort of very elementary steps here and there. And essentially what we're going to be left with is something like this. Rho B, okay, sorry, UB minus UU, okay, is equal to rho U minus rho B, UU minus WN, okay? So I'm just skipping a couple of steps here. And if you remember the definition of the SL, okay, which is VN plus, so it's essentially UU minus WN, okay? What you have here is essentially the burnt density times the jump in velocity is equal to the difference, okay, in densities times SL, okay? If you divide by rho B, then you have your basic expression, which is sigma minus 1 SL. What's sigma? Sigma, by definition, is the jump, essentially, in density, okay? Now, typically, sigma for a premix flame ranges between 5 and 10, okay? So you have a substantial here jump, okay? So here you can write down as UB minus UU is equal to sigma SL minus SL, right? And so essentially what this is telling you is that the unburnt velocity in a wave stationary is SL, and the downstream, okay, velocity is sigma times SL. So there's an acceleration, okay, downstream of the premix flame, which is essentially 5 to 8 times, or 5 to 10 times, sigma times the value of the unburnt density. Remember that SL will be from very small, okay, to about 1 meter per second. So very, very small, so 1 centimeter to 1 meter per second. So it's extremely slow compared to, say, the speed of sound, okay? This is the the jump in velocity. The pressure jump, to be honest, I'm going to be very, very fast, but take the momentum conservation, which you write in terms of like this, P plus rho U Vn, okay? The jump of this quantity is 0 across the flame, where by definition Vn, remember, was Un minus W, okay? I will skip, so you essentially substitute this quantity here, expand the jump operator, okay? And you'll get something like this. Okay. Sorry, it's not equal here. So again, feel free to actually fill in the gaps here as an exercise. Sigma 1 over sigma UB minus W, okay, is equal to PU over rho U plus U, and then UU minus W, okay? We do the same kind of thing that we did before, so SL, remember, is UU minus W, and from the jump in velocity, we substitute for UB sigma minus 1 SL plus UU. Okay, you substitute in this in the above expression, and what you get essentially is PB over rho U minus PU over rho U, okay, is equal to minus SL times the jump in velocity. So essentially, the jump in pressure, okay, is something like this. Rho U SL jump in velocity, which when substituted is minus rho U SL squared, which is pretty familiar, sigma minus 1. So what this is telling us is that the jump in pressure for the 10th time we're saying this is very small, because SL clearly is very small. So SL squared is extremely small, okay? In fact, you can even write this SL squared as the speed of sound in the unburnt times the Mach number squared, and this is gamma RTU, okay, the speed of sound times mu squared. So the jump in pressure, okay, can be written as essentially, if you substitute for SL squared, okay, you can see that it's essentially minus gamma PU mu squared sigma minus 1. So again, we find that the jump in pressure is really of the order of the Mach number squared. So it's a very, very small jump, okay? The hydrodynamic pressure does change, okay? But the jump is extremely small, because the Mach number is very small. Okay, so that's the first level of detail. Now, what we want to do now is move closer. So we have number 2, okay? the transport, the preheat zone. We want to move a little closer now to the flame and see or reveal essentially the first additional phenomenon that we cannot see with the Rankine-Hugoniot approach, which is essentially diffusion. Now, the first thing, of course, that we have to understand is that both, in these cases, diffusion and convection obviously is very slow convection because the Mach number is so slow, are generally slower or slow processes. They are slower processes with respect to reaction, okay? So essentially the reaction time, okay, is generally much, much smaller than the convection and the diffusion, okay, time scales, okay? This means that both diffusion, okay, and convection occur on much larger time scales. So the length of the reaction zone is actually much, much smaller than some, say, a convective, whatever that means, length scale and a diffusive length scale, okay? Now, obviously, this, let's say, I will put in parentheses because the convection, per se, the convection length scale doesn't really have any meaning in the sense that you can have for example, a uniform flow, okay, where you have a convective flow, which is infinitely long, okay? So you can make the convection length scale, let's say, as long or as small as you want. But clearly not the diffusion length scale, in the sense that the diffusion length scale will be related to essentially gradients, okay? So let's say you have now your spatial dimension, okay? What we can do here, you can still have an interface, okay? And we're going to say that this interface now is of zero thickness, but it's only going to be related to the reaction zone. So it's a reaction zone of zero thickness, okay? So this is where all the chemical reactions take place, okay? On the other hand, we have upstream here a so-called preheat zone, okay, which is of a length scale, of a diffusive length scale, so preheat zone, okay? So this is still a sheet, the reaction zone, but not the preheat zone, which has a finite thickness, okay? So the difference between what we had previously is that now all the functions, the temperature and the concentration, are going to be continuous. So you have essentially a temperature, for example, which starts here, okay? And we're going to see a gradient of, again here, this is why I've been so slow in this course. A gradient of temperature, which is going to gradually, uniformly grow from TU to the final value, which is the adiabatic flame temperature, TB. You see that now there's no jump. There's a continuous function of temperature, okay? The same, and clearly not, the function is not continuous in terms of the derivative, okay? The derivative will not be continuous. You see here there's essentially a jump in the in the derivative, okay? But the actual temperature function is going to be continuous. Now, you can also look at the deficient reactant here, which will gradually be depleted until it's identically zero downstream. Okay, so downstream we have YB equals 0. Okay. So the derivatives of these functions are not continuous because there's going to be a jump at the reaction sheet. So let's write it. This is the reaction sheet. The function of this reaction sheet is that it will essentially fix the downstream boundary. The downstream boundary is temperature equals TB and YB equals 0. Okay. Clearly, the upstream boundary is going to be fixed by the inflow. Okay. So, in some sense, I hope you can see this. The reaction sheet, okay, will act as a sink. I hope you know what that means, okay? It's the opposite of source for the reactant, the deficient reactant. So it will kind of, here, it will deplete it so as to make sure that anything downstream is going to be 0, okay? So in some sense, because you have that condition, and of course it's going to be a source of temperature because it's an exothermic reaction. So this level of detail means essentially this, that the reaction sheet, we cannot see anything that happens within the reaction sheet. It's too thin, okay? So it's 0 thickness. But it does fix all of the downstream conditions. So in fact, it will be the cause or the source of gradients, okay? Because clearly we have a situation where far downstream here, the conditions are fixed by the reaction sheet, and far upstream here, the conditions are different, and they're going to be fixed by the inflow. So in between, you're going to have essentially the onset of gradients, okay? And when you have gradients, then you have essentially transport of some sort, especially diffusion, okay? So gradients of reactant and temperatures and temperature are established, okay, in the preheat zone. And of course, they will activate, as I said, mass diffusion fluxes, okay? Of course, convection occurs because you have essentially a velocity here, u, okay? So we can think of this velocity as being, again, uniform, okay, in the preheat zone, and then there's going to be a jump, okay, in the burnt zone. But clearly, the reaction, because it occurs in a sheet of 0 thickness, is not going to be present when we write down our equations. So if we write down our equations, okay, let's write them down in steady state. Okay, we're going to have, well, a balance between the convective aspect, so du. So let's look at the temperature equation still. This is a convective term, okay? This is going to balance, because we are at steady state, okay? The diffusive term, which will be, well, a mass diffusivity, sorry, a thermal diffusivity, sorry, not a mass diffusivity, times the second derivative, okay? So this is essentially the divergence of a gradient. So we're using essentially the Fourier law to establish this, plus let's say 0, okay, in the sense that this will be to remind ourselves that this is the reaction, which we cannot take into consideration because in the preheat zone there is no reaction, and here it's just 0 thickness, okay? So there is a complete balance between convection, okay? Let's write it with the letter C, okay? And diffusion. And they balance out, okay? For the species, it's going to be very similar. So we have a convection of mass fraction, okay? And then a mass diffusivity this time, and then the second order derivative, okay? Now, if we look at these terms, okay, I hope you remember, like we have derived, if you look at the very early stages of the reactive flow, the third part of the course, we derived these equations, okay? So go back and we derived them. There is going to be clearly a rate of change here, a time derivative, which we have dt by dt, but clearly we have set this to 0 because we're at steady state, okay? So in the preheat zone, there's a balance between convection and diffusion. We can also take a look at the signs here because look at the positive x. So u here in the preheat zone is positive, right? In the growing x. So this quantity here, u, is positive. Okay. Also, the gradient of temperature is positive because in the preheat zone there is an increase in temperature clearly because we said that the reaction zone actually is a source, okay, of temperature. So it will essentially increase the temperature. So you can see that this means that the second order derivative, okay, is positive. Okay. So that's why you have this form here with it's essentially concave in this direction, okay, the temperature from TU to TB. Okay. On the other hand, you still have a positive velocity, but on the other hand, you have a decrease, okay, of the fission reactant until it's 0. So this quantity here is negative. And so the second order derivative is negative, and so the profile will be concave, but in the other direction. So between yu and yb equals 0. Okay, so that's why I've drawn these profiles in this form. Okay. Let's see what else we can see. Well, if it's relevant here. Well, remember that by Fourier, essentially, we can use the flux and temperature. Usually it's Q, right? Let's use the J to have both the same notation for temperature and species. In the case of the heat flux, we have essentially a minus sign and then conductivity and then a gradient of temperature, right? In this case, for the species, we have essentially a very similar thing with Fick's law, and it's minus a diffusivity, let's say and a gradient of of species. Now, clearly, the gradient of species we said is negative, so this flux is positive, okay? So essentially we have a flux in this direction, a diffusive flux, okay, in the same direction as the velocity, so as the convective flux, okay? For the temperature, this is positive, the gradient, so the flux is in the opposite direction. Okay, so this is the flux and temperature in the opposite direction of the convection. Okay. So essentially, you have these three phenomena. Let's have, well, I was supposed to do it on the same level, but anyway. So you have a convective flux of temperature and species, okay, given by U, which is always in the same direction. But now you have a diffusive flux of temperature going from the hot to the cold side. So what you see is, that's why it's called the preheat zone. You have essentially the burnt side heating through diffusion, okay, the cold side, okay? So this is essentially how the the flame propagates, okay? It propagates essentially by heating up this incoming fresh mixture until it burns through a reaction, okay? In this case, it's burning in this very small sheet, okay? So in order to remind ourselves that there is also a reaction in here, we can say that there is a source for temperature here. So there's a source of temperature, okay, keeping the temperature high, and eventually it's going to diffuse, okay, in this direction against the upcoming velocity, so the convective flux. So you see that if the convective flux is, for example, too large, what may happen is that the diffusion, okay, will not be capable of heating up the mixture, okay? And so we won't be able to stabilize this flame, which will be blown, okay, in this direction. On the other hand, you can see that if this velocity here, the convective velocity, is zero, what you will have is essentially a propagation in this direction, because we will want to heat up fresh mixture. Okay, so the fresh mixture ahead of the flame will increase its temperature and will eventually burn. So this sheet, reaction sheet, will be propagating in this direction. So that's why you essentially have one propagation speed, okay? Now, for reactants, again, you have the reaction acting as a sink, in the sense that it's depleting, okay, the flammable mixture, the species, okay? It's essentially keeping this gradient, okay? Both of the fluxes now are in these directions. So the function of this sink here, the reaction, is to deplete all of the species that is coming from the left, essentially. Okay. One last thing that we can say is, usually we deal with non-dimensional quantities. So if you non-dimensionalize temperature, for example, you can non-dimensionalize temperature, defining the non-dimensional temperature as T minus Tu divided by Tb minus Tu. This is simply to say that this varies between 0 and 1, okay? It's 0 when T equals TU and 1 when T equals TB. And Y non-dimensional is non-dimensionalized with respect to TYB. You can still hear me, right?
Sì, sì.
Okay. And if you plug in these definitions into the equations, the steady state equations, okay, you will have, well, let's put back the non-stationary term as well. You have a temperature equation with a convection term and a diffusion term with nothing in front, okay, plus 0. And this is still non-dimensional. And the species equation will be very similar, dy tilde, but so u tilde dy by dx, okay? But the only difference is that you have a coefficient here, which is the reciprocal of some non-dimensional number, which we call the Lewis number, okay? I'll tell you what it is in a second. And then you have the second order derivative. What the Lewis number is the ratio of a thermal diffusivity, which is defined as lambda is K, okay, is what I call K, is the conductivity, thermal conductivity. So it's lambda divided by rho Cp, okay, and the mass diffusivity. So essentially is the ratio of the thermal diffusivity to the mass diffusivity. So this is the thermal diffusivity. So it measures essentially how efficient, okay, the diffusion of heat is compared to the diffusion of mass. Now, if the Lewis number is generally bigger or smaller than 1, what you have here is you have an imbalance between these two gradients. So you will have something like this, for example. I don't know if you can see it, but the gradients, for example, of temperature will be, for example, smaller than the gradient of concentration, okay, of deficient reactant. The Lewis number has several effects, okay? Unfortunately, we don't have time to discuss this, but the fact that mass and heat don't diffuse in the same way, but one diffuses better than the other, is a source of so-called thermal diffusive instabilities and so on. If you look at the first page of our classroom, okay, the combustion classroom, what you have seen, you can probably take a look now. You know what I'm talking about, the Google Classroom, right? So on the first page, I have added a picture, okay? Now that picture is a simulation that we did, okay, with the code that we have in the department of a premix flame. As you can see, it's a very thin, okay, layer. What you can see there is essentially the reaction rate, so it's the reaction layer. But you can see that it's all curly, okay, it's all kind of corrugated. Well, the reason for that is that the Lewis number is quite substantially smaller than 1, okay? And you can have this, for example, with hydrogen mixtures or hydrogen-enriched mixtures, because hydrogen essentially has very high, okay, diffusivity, because it's a very small molecule, okay? So it diffuses very rapidly, okay? It's called a high mobility. okay? So usually when you have hydrogen mixtures, you have Lewis numbers that are smaller than 1, okay? And there is a mechanism for which a planar flame loses its stability, its planar stability, okay, and creates these cellular structures. Very interesting, and it's also quite relevant to hydrogen combustion, which is the new hot topic in this field, as you know. Now, clearly, when the Lewis number is equal to 1, you can see that the two equations are exactly the same. Okay? What do you think that will lead? Well, it will lead to the fact that essentially the profiles are going to be exactly the same. So actually, let's, okay. Well, I made a mistake here because I shouldn't have, okay. So let's see if I can do this. So if this is the profile of temperature, okay, obviously we're talking about non-dimensional quantities. This is going to be the mirror image is going to be the, maybe I saw, well, maybe I have succeeded, okay? So you see that the profile of temperature and the profile of concentration of the efficient reactant are essentially one, the mirror image of the other, because the equations are exactly the same, okay? What is not the same is the boundary conditions, okay, for the two. Good. Okay, now let's finally get to the final third. Well, it's not moving, okay. To the third level of detail, okay? The complete flame structure. So now what we do is we get even closer to the flame, right? So you still have a direction here. What we saw before was a preheat zone. Okay, now we're going to have a smaller zone, okay, which is our reaction zone, okay? So now finally we have unveiled all of the levels of detail, okay? The preheat zone, and now we're also looking at the reaction zone. So what's going to happen here? Well, as before, we have an unburnt temperature. By diffusion, the temperature will increase, okay? Now you see that at some point, it will reach a value which we call Ti. Now, why I? Well, because you know that reaction rate is activated only when the temperature is quite close to the maximum temperature, right? So this is an activate or ignition temperature at which is high enough so that the reaction rate, okay, is, let's say, non-zero, okay? So in here, the reaction rate, omega, is 0, okay? Here, it's clearly non-zero. And this temperature is quite close to the final temperature, so we're going to draw it quite close to TB, okay? On the other hand, we have the reactant, okay, which again is depleted, but not completely, okay, in the reaction zone, okay. So the decrease here is due to diffusion. Now we are actually depleting it also through reaction. So we have essentially YB equals 0. Reaction, okay, is essentially what? A function of what? A function of temperature through the reaction constant, and then there is going to be essentially a dependence on the how do you call it? The concentration, right? So in this point here, at the beginning of the reaction is going to be identically 0 still, and it's going to increase because of the increase of temperature here. Okay, so due to this term here. But as you can see, as the temperature increases, the reactant also decreases. So there is going to be a peak, and at some point it's going to go down, not because the temperature is not high, the temperature is the highest, but because the reactant is actually being depleted. So this is essentially the form of the reaction rate. Okay. The form of the reaction rate. Let me as we said, this is the thickness LR, and this is the thickness of the diffusive layer or the preheat LD. Okay. We've also said that in the preheat zone, there is a competition between convection and diffusion. Okay. Okay. What else can we say? Well, we can say that the reaction, okay, zone has a thickness which will be essentially measured in the time scale, okay, of the reaction times a convective velocity, which is UU, for example, okay? And so it's essentially a reaction time times SL, okay? And the diffusive thickness will be essentially a diffusive time scale times SL. Because clearly the reaction time is much, much smaller than the diffusive time, clearly we have that LR is much smaller than LD, okay? In the next lesson, we're going to look at how to estimate the ratio of these two, okay, rigorously. Now, the reason why, the fact that the reaction zone is very, very small, and the fact that we expect, as you can see here, look at the reaction rate, okay, we expect, for example, intermediate species to vary extremely rapidly, okay? Clearly now, what is going to be the dominating factor, the convective or the diffusive transport? Well, think of this. Unfortunately, I can't, okay. The diffusive transport in the reaction zone is going to be essentially of the order of, well, some variation of the property, for example, of concentration divided by what? Delta x squared, right? Because we're dealing with essentially second order derivatives. So for example, we can say it's a variation over LR squared compared to say the convective transport, which is essentially of order delta y over delta x. So essentially delta y over LR. So as you can see here, this is the dominating term because LR is very small. So very small squared mean at the denominator means that it's very big. So in fact, what we expect here is the diffusion, okay, aspect to dominate over convection, okay? And obviously, there's going to be also reaction. So essentially, you have two zones. One is bigger, one is thinner. One is the preheat zone when you have an interplay between convection and diffusion and no reaction because the temperature is too low. And then in the reaction zone, you finally have a reactive, okay, phenomena, which essentially will be balanced by diffusive fluxes, okay? Whereas convection is generally less relevant, okay? And this is also quite important to remember. So remember this, okay? These two, convection and diffusion in the preheat zone and diffusion and reaction in the reaction zone, okay? Well, of course, now we ran out of time. But we still need at least one lesson. So let me just recap in these 2 minutes if I have the, okay. So the structure of the flame, therefore, is the following. So we have a preheat zone, a reaction zone, and then this is a schematic, and then downstream conditions. So burnt condition, and an upstream condition, right? Which is the fresh mixture, okay? So the boundary conditions, BC, are unburnt or upstream temperature and concentration. Downstream, you have essentially TB and YB, which is equal to 0. Now, in the preheat zone, we said that there is a balance between convection, okay, and or we can even put a minus sign here if you want, or whatever. Let's put a minus sign. It's not working. You're still with me, right?
Sí, sí.
Sí, sí.
Yeah, it's telling me to clear the canvas, but I can't now, obviously. Okay. Minus sign and the diffusive term, okay, equals to 0, so there's no reaction. For the species, again, is this, the convection, and then we have the coefficient 1 over Lewis number, okay, and the second order derivative, okay, of the species equals to 0. In the reaction zone, we have an interplay between the diffusive term, okay, and reaction, okay, which we write like this, omega. And again, minus 1 over the Lewis number, that's the Lewis number, second order derivative, equals the reaction, okay? So that's what essentially we have. Next time, and this happens in the thickness LD, and this in the thickness LR. okay? And obviously, LR is much smaller than LD. I haven't, it doesn't show here. Now, next time, we're going to find essentially an expression for the ratio of LR over LD, okay? What does this ratio depend on, okay? And we're also going to find an expression for SL, answering the question, what does SL depend on? Because if you remember, all of this could not be done with the Rankine-Hugoniot analysis, okay? So I'm going to see you for maybe the last time. Obviously, it's not going to be enough. Next time, maybe I'm going to use also Friday. You have to excuse me, but it's much slower with this method, with the blackboard like this for me. One other thing for the exam, I just want to tell you that if you're planning to take the exam, okay, at the beginning of June, I'm still waiting for them to assign me a classroom, a room, because I have to be in this room, okay? Because generally speaking, it's going to be in person. So I don't know if you've seen this this form, online form, il modulo, whatever. L'avete visto voi? The form that you have to fill in to tell me whether you will come in person or whether you will stay at home and carry out the exam remotely. Apparently, you're going to have to justify the reason why you're staying home. Okay. I hope you've understood this.
Sì, chiaro.
Okay. And also for this foreign students, okay? I'm going to stop recording here.